Hello, we're Team Indium, and our topic for this project was high temperature superalloys. So we decided to go with Haste Alloy X because it is really resistant to heat changes and really resistant to oxidation. This makes it ideal for use in jet turbines because those are exposed to extreme temperatures and stress for extended periods of time. So for the properties, you can see here are the top 4 contributors to Haste Alloy X. As you can see, we have sketched out the stress versus strain diagram, and you can see it just on a normal day, room temperature, how much strain or how much stress that Haste Alloy X can take before it strains. And then at high temperatures, which is about its operating temperature, how that value decreases but does not go all the way down.
Okay, and now I'm going to talk about how the structure leads to our desired material properties for our application. Since our alloy is in a crystal structure, it leads to phonon lattice interactions. Since it's a metal, it has free electrons in the conduction band, meaning that it has a high dispersion of temperature and a high resistance to temperature change. And since in our application, it's going to be a lot of heating and cooling, and the high resistance to temperature change prevents creep.
Haste Alloy X is made up of 47% nickel, as we said before, which takes place in the FCC phase, or FCC structure, and the rest of the metals that go into its makeup have the BCC crystal structure. So whenever it is melted at a very high temperature and mixed together as a solution, as it cools, it takes 2 different solid phases, and that leads to the different grain boundaries that you'll see here. So we'll have some in the FCC phase, and then this one might be in the BCC phase. And that all comes together to create the metal or the alloy that is Haste Alloy X.
Okay, so now we're going to be talking about how Haste Alloy X is processed. So the old and still used in many applications method is just dumping all the different components of Haste Alloy X, melting them down, and then letting them cool. That is the quickest and cheapest way to create Haste Alloy X. But the newer technology is selective laser melting, or SLM. It's basically building up the alloy layer by layer, and this helps to just precisely select where you want to place each different kind of metal. It lets you minimize unwanted phases, and it lets you maximize the desirable properties of the metal.